In level flight, at steady speed, lift equals weight and thrust equals drag. Lift and weight are about 8 times greater than thrust and drag, but for clarity's sake, we've reduced this ratio in the diagram. So we have two unequal pairs of forces acting at right angles to one another. But suppose we want to climb or descend. What happens to the forces then? As the nose pitches up, the picture changes. 3 of the forces, lift, thrust, and drag, are in the same relationship to the flight path in the climb as they were in level flight. Weight, however, still acts vertically downwards, and so is now at an angle to the flight path, downwards and backwards. It is thus augmenting drag. This directional effect of weight on drag slows the aeroplane down in the climb, so that both lift and aerodynamic drag are reduced. But if we add the drag effect of weight to the remaining aerodynamic drag, the total drag becomes greater than in level flight. To keep the forces in balance, thrust must be increased to balance the new force of drag plus its component of weight. Change from a climb to a descent, and weight, still acting vertically downwards, is now augmenting thrust. The aeroplane will accelerate, lift and drag will increase. So to keep the forces in balance, we must reduce thrust to allow drag to balance the force of weight acting forwards down the flight path. We can experience these forces physically by riding a bicycle up and down a hill. Going uphill, we must increase thrust to balance the proportion of our total weight acting backwards down the hill. If we shed even a small fraction of that weight and deprive it of thrust, we can see what happens to it. Going downhill, the opposite applies. We have to reduce thrust to avoid excessive speed, and the discarded weight will continue forwards down the slope. Once we leave the ground behind, however, no matter where we point the aeroplane, one of the 4 forces acting on it, weight, always acts in one direction, straight down. All the rest of the geometry of flight revolves around that central fact. And so, when we want to climb, we have to offset the effect of weight acting partly backwards down the flight path by increasing thrust, just as we have to pedal harder to ride a bicycle up a hill. When we want to descend without increasing speed, we have to offset the effect of weight acting forwards along the flight path and decrease thrust, just as we have to on a bicycle going downhill. Beyond a certain angle, the descending flight path becomes a glide. There is now enough weight acting forwards along the flight path to keep the forces in balance, and thrust as such is no longer needed. Even in this situation, the forces remain in balance and a steady speed is maintained on the glide path. But the proportion of weight acting forwards along the flight path is now sufficient to act in place of thrust from the propeller and to equal drag. As soon as the aeroplane is leveled out again and power is restored, the 4 forces resume their normal pattern for steady level flight.